Hello, Anacortes High School Geometry. Welcome to week 7 of new content. This week, we're going to be talking about some of the things we can do with regular polygons. Now, what does it mean when I say regular polygons? Well, regular polygons are figures that have 3 or more sides, and they are regular. They are what most of us would conjure up as images of a pentagon or a hexagon or an octagon. Mathematically, they are polygons where all the side lengths are the same and all the angle measures are the same. Okay, to use geometry terminology, all of the side lengths within a regular pentagon are congruent and all of the angles within a regular pentagon are congruent. Okay, so that means in a regular pentagon, all 5 side lengths are congruent and all 5 angle measures are congruent. In an octagon, all 8 side lengths are congruent and all 8 angle measures are congruent. All right, so we're not really interested too much in just regurgitating a definition of regular polygons. We want to be able to do things with them, okay? And one of the first things we want to do is recognize that they have a center, okay? There is a point within each of these regular polygons that is the same distance from all of the vertices. Okay, and if I draw a segment from each vertex to the center, I get this one point in the center, and I see a bunch of angles that are formed there. We call those central angles. All right, now what is the measure of a central angle in a given regular polygon? Well, it depends on the number of sides. I know that rotating all the way around at a given point is 360 degrees. And at this central point, the central angles completely fill that 360 degrees, okay? So in the instance of a square, the 4 central angles must add to 360. They also must be congruent to each other. So we take the 360, divide by 4, and we get 90. With the pentagon, we take the 360 and we divide by 5 because there are 5 central angles. The number of central angles is always equal to the number of sides. 360 divided by 5 is 72. With a hexagon, the 360 divided by 6 is 60. With a heptagon, divide 360 by 7 and we get about 51.4. Rounding to the nearest tenth is going to be fine for today. And a regular octagon, we take the 360, divide by 8, and we get 45. All right. We are also interested in what each of the interior angles is. In a square, it's obviously 90. That's one of the things that defines a square in the first place. But what is it with a pentagon? I have 5 angles in a pentagon. What is the angle of, or what is the measure of each of those angles? Okay, it says right here it's 108, but how did we get there? How did we figure that out? Okay, well, one strategy that I think illustrates pretty clearly where we can get the sum of the angles within a regular polygon and then figure out what each angle has to be is to start at one vertex and draw all of the diagonals. Okay, so in all these diagrams, I kind of started in what was kind of the lower left and I drew diagonals. Diagonals can't go along the side, but they can go to all the other vertices. Okay, I did that with the square, I did that with the pentagon, I did that with the hexagon, the heptagon, and the octagon as well. And what that does is it creates triangles. In the case of the square, it creates 2 triangles. In the case of pentagon, it creates 3 triangles. Hexagon, 4. Heptagon, 5. Octagon, 6. So you may have noticed a pattern. When I create these diagonals, we are always creating a number of triangles that is 2 fewer than the number of sides in the figure, right? The square has 4 sides, 2 triangles. The pentagon has 5 sides, 3 triangles. Triangles are nice because we know a lot about them. Each of these triangles has 180 degrees as the sum of its angles, okay? And every angle inside these figures is completely filled up by angles from these triangles, okay? So if I take a look at the hexagon, what do the 6 angles of a hexagon have to add up to? Well, they have to add up to the same number of degrees as are in the 1, 2, 3, 4 triangles, okay? So 180 times 4 is 720. Divide that by the 6 angles that we have here, and that's where 120 comes from. With the pentagon, 1, 2, 3 triangles, okay? 3 times 180 is 540, divided by the 5 angles that we have, and that's where we get 108, okay? So the number of triangles in each figure is always 2 less than the number of sides, and the sum of the angles in each triangle is 180 degrees, okay? Each angle in each of these regular polygons is completely filled up by triangle angles, so the sum of the angles in each figure has to be the number of sides minus 2 times 180, then divide by the number of sides slash angles that you're dealing with, and you get the measure of each angle. All right, now we're going to take a look at how we can find the area of one of these regular polygons. A square, that's not too challenging. We know how to do that. But what about the area of a regular pentagon or a hexagon or a heptagon or an octagon or a 9-sided figure, or a 10-sided figure, however many sides we want to work with, okay? We're going to use the shapes inside of these figures that we can already see, that we already know a lot about, triangles, okay? In the instance of a regular pentagon, I can see 1, 2, 3, 4, 5 triangles, and they're congruent to each other. How do I know? Well, all of the side lengths are the same, and all of the angle measures are the same as well, okay? The length of the segments connecting the vertices to the center are the same. I can get at triangle congruence a number of ways, but these 5 triangles are congruent. So if I find the area of one of them, I just multiply by 5, and I can have the area of the entire pentagon, okay? Now, this presents us with a challenge, because to find the area of the triangle, we need to follow the formula for an area of a triangle. 1/2 times the base times the height. Well, the base is just a side length. So if we're given a side length, that's nice. We already have that. What's the height of that triangle? Okay. That's something we usually don't have, but it's something we can find. Okay. And this height has a special name for it. It's called the apothem, and it's the distance from the midpoint of a side in a regular polygon to the center, and it forms the height of these triangles that we're going to find the area of. All right, now how can we find the apothem? Well, the answer there is trig. If we go back to the diagram we just looked at, you'll notice that the fact that the apothem is perpendicular creates a right triangle that we can work with. And there was a reason we just laid out how we can find central angles and interior angles, because now I can use those to find angles within the right triangles and use those to find the apothem and go from there, okay? All right, so as an example, let's take a look at a regular heptagon. Heptagon has 7 sides, and let's just say, for the sake of this example, that the side length is 6. Now, as we saw earlier, each central angle is 51.4 degrees, so 1, 2, 3, 4, 5, 6, 7 of them. And each interior angle, rounded to the nearest tenth, is 128.6 degrees. That big angle right here is 128.6. Now, the right triangle I'm going to work with is right here in orange. Okay, I pulled out a little sketch of it. And if the side length of the heptagon is 6, that means that this base right here of the right triangle is half of that. It's 3. Okay, this interior angle right here is the 128.6. For the right triangle, I cut that in half, 64.3. And my central angle, formed by the 2 dotted red sides, that's the 51.4, cut in half, and I get the 25.7 up at the top. Okay, I can use either one of those angles along with the 3 to find the apothem using trig. Okay, if I'm using 25.7, the 3 is the opposite side and the apothem is adjacent, or if I'm using the 64.3, the A is the opposite side and the 3 is adjacent. So I have these 2 options. Tangent of 64.3 equals the opposite side of A over the adjacent side of 3. Multiply both sides by 3, and we get an apothem height or length of 6.2. I could also go tangent of 25.7 equals 3 over A, multiply both sides by A, divide both sides by tangent of 25.7, and we get the exact same apothem height, 6.2. Okay, you don't have to do it both ways. Choose one or the other, whichever one seems easier to you. Okay. All right, the whole point of finding the apothem was so that we could find the area of this green triangle right here, okay? 1/2 times the base of 6 times its height, which is the apothem of the heptagon of 6.2, comes out as 18.6. So that's the area of the green triangle, But remember, we want the area of the heptagon. There are 7 congruent triangles, or 7 triangles that make up this heptagon, and they are all congruent. So we take the area that we just found, the 18.6, multiply it by 7, and we end up with 130.2. All right, last thing for today. What if we take one of our regular polygons and we circumscribe it inside of a circle? Okay, that means that there's a circle that has the same center as the center of our regular polygon, such that the circle goes through all of the vertices. Okay, in this case, we have a regular hexagon, and the circle that goes through all of its vertices has a radius of 5. And what we want to know is we want to know the sum of these shaded areas. What's left over if I carve out this regular hexagon from the circle that has a radius of 5? Well, to figure that out, we're going to need to know a couple of things. Okay? We're going to need to know the area of the circle, we're going to need to know the area of the hexagon, and then we're just going to need to know the difference between the two, right? What is this? What are the shaded areas? What's the area of the circle minus the area of the hexagon? All right, area of the circle is pi times the radius squared. So pi times 5 squared, which is 25 pi, which is about 78.5. The area of the hexagon, as we just saw, takes a little bit more work. We're going to have to create one of these right triangles, okay? We have this, in this case, hypotenuse of 5. And we need to know the apothem and this base right here, okay? Well, I can set up my trig equations, right? Sine of 60 is equal to a over 5, multiply both sides by 5, and I get 4.3 for the apothem value. I can do cosine of 60 equals b over 5, multiply both sides by 5, and I get 2.5. Oh, okay, if this was a 60-degree angle, and there's a 60-degree central angle, this is actually an equilateral triangle, so this, the side length of this hexagon actually has to be equal to the radius. That's kind of a cool thing. Only happens with hexagons, though. All right, so now I can find the area of this blue triangle, 1/2 base times height, 1/2 times the base of 5 times the height, which is equal to the apothem of 4.3, which comes out as 10.75, okay? So the area of the hexagon is going to be 6 of those 10.75 area triangles. 10.75 times 6 is 64.5. Now, at this point, we have to remember, what were we actually trying to find? Well, we were trying to find the shaded area. And the shaded area is the area of the circle minus the area of the hexagon. Well, the area of the circle is 78.5. The area of the hexagon is 64.5. The difference between those is 14. And there you have it. All right. As always, if you have questions as you're doing the homework or preparing yourself for the quiz, feel free to contact either Mr. Holgertz, Mr. Nichols, or myself. And best of luck. Enjoy.